This lecture is for ELEC 1510 Logic Design. This is Lecture 13, Part 2 on Behavioral Verilog Case Statements. This is information from textbook section 4.12. In this video, I'm going to talk about designing a 4x1 multiplexer using Behavioral Verilog case statements. Just to remind everyone what a 4x1 multiplexer looks like, here's the diagram. We have 4 inputs, A, B, C, D, 2 select lines, S1 and S0, and 1 output Z. The inputs A, B, C, and D are routed to the output depending on the state of the select lines. So if select 1 is 0, select 0 is 0, then A, corresponding to 0, 0, is routed to the output. Now if select 1 is a 1, select 0 is a 0, then C, corresponding to input 1, 0, is routed to the output. So the Boolean expression that we can write to define Z in terms of all of the inputs looks like this. Z equals S1 prime S0 prime A plus S1 prime S0 B plus S1 S0 prime C plus S1 S0 D. If we want to write that instead as a bunch of if statements, it'll look like this. This is not a Boolean expression anymore, but it will translate more directly into Behavioral Verilog case statements. So if S1 equals 0 and S0 equals 0, that means that Z is equal to the input A. If S1 is equal to 0 and S0 is equal to 1, then Z is equal to the input B. And so on until we get to if both of the S select lines are 1, then Z is equal to the input D. So Behavioral Verilog case statements work like this. After the input-output declarations, and after you say always at symbol and then list the input variables, you'll have a case statement and then in parentheses the variable of interest, which can be a multi-bit variable. In the case of our 4x1 multiplexer, the select line S is actually comprised of 2 bits. After that declaration, you actually start to list the different cases that that input variable can take as n prime b and then the case. So n is the number of bits in the variable of interest. So for our switch line S, it's 2 bits, so we would have 2 prime b. So in that case, n would be a 2. And then variable state, so presumably the first state would be 0, 0, so we would list 2 prime b 0, 0, colon, and then an output declaration. So then we would say Z equals A. Then you keep listing cases. N prime b, again n is 2 in this case, so 2 prime b state 2, the second state is 0, 1, colon, Z equals B, and so on. We would have 2 prime B 1 0 and then Z equals C, and 2 prime B 1 1 colon Z equals D. Then finally you end the case statement with the declaration end case, and then you end the module unless you have more to put in the module. In total, the declaration for the 4x1 multiplexer is going to look like this. We declare the actual module mux 4x1 I'm calling it, with variables S, A, B, C, D, and Z. We have an input with 2 bits called S, so that will comprise the 2 switching lines for the 4x1 mux, S1 and S0. Then we have 4 inputs, A, B, C, and D, that are 1 bit each, and 1 output reg for register, output reg Z. Then we'll say always at symbol, A or B or C or D or S, those are all of our inputs. There's no semicolon at the end of that line. Then we'll say case s. S is the variable that has different cases that determine what the state of the output is. So that's the one that we're going to use in our switching statement. The first case is 2' B00. Again, the 2 is for the number of bits that S has. So 2' B00, that's the first case, Z equals A. Then 2' B01, colon, Z equals B, semicolon. 2' B10, colon, Z equals C. And 2' B11, Z equals D. End case and end module. And this is a behavioral declaration using a case statement for a 4x1 multiplexer. This is what that code looks like written as a module in Quartus. So this is the exact same code from before. And here is that module being simulated. So in this simulation, first I have the switching lines S, which have S1 and S0 set to 0, 0. Then I set them to 0, 1. Then I set them to 1, 0. Then I set them to 1, 1. Now, to prove the behavior of this multiplexer, I'm sending different clock signals with different periods into the inputs A, B, C, and D, so we can tell which one of those inputs is being routed to the output at any given time. So let me block off the different regions of time when the switching lines have different values. So when the switch lines have value 0, 0, A should be routed to the output. And we can see that if we cross off B, C, and D, A and Z are equal to each other. Now when S is equal to 0, 1, you can see that B is being routed to the output. When S is equal to 1, 0, C is being routed to the output. And finally, when S is equal to 1, 1, D is being routed to the output. So the module works as we would expect. And so this can sometimes be a simpler way of writing the behavioral instantiation of module subblocks rather than using gates or Boolean statements.